all they have as physical input is electricity. Well, let's just use that to harness and keep track of information. Let's store a little bit of electricity when we want to represent a 1, and let's let go of that electricity in some sense when we want to represent a 0 instead. And so because the input to computers is so simple, thus gives us these zeros and ones that we now use, but we seem to have created a problem for ourselves. If we only have one light bulb or one switch, if it's off, it might be a 0. If it's on, it might be a 1. But how do I count higher than 1? That problem still fundamentally remains. Well, I could, of course, use more light bulbs. So let me ask this. If we were to use 3 light bulbs, how high could we count? So with 1 light bulb, we can count from 0 to 1, 2 possibilities. But with 3 light bulbs, how high could we count? Well, let me go ahead and ask this question here on the screen. In just a moment, you'll see on your side this particular question via which you can respond on your device. How high can you count with 3 light bulbs? So instead of 1, I give you 3, each of which can be on or off. How high can we perhaps count? So you'll see on the screen here, the answer is coming in. We have a lot of folks thinking 60+% that it's 8 is the highest you can count. A lot of you think it's 7, and some of you also think it might be 3 or 2. So that's actually an interesting range of answers. And let's see what might actually be the case. Well, let me cut back over to 3 actual light bulbs here, all of which are off. And most naively, I think if we were to turn these light bulbs on, if they currently represent 0, obviously I could turn 1 on, and we could call it 1. Then I could turn the second one on and call it 2. Turn on the third one, and now with all 3 on, we could say now we're representing 3. But we're not really being clever enough just yet if we're only counting as high as 3, because I'm just turning them on in this story left to right. But what if we were a little more clever? Maybe we turned them on right to left, or maybe we kind of permuted them in different directions. That is, we took into account not just how many bulbs are on or how many fingers are in the air, but rather the pattern of on and off light bulbs that we've created. So let's just count this up. So let me somewhat systematically turn some of these bulbs on here, albeit virtually. Here might be 1. Here might be 2. Here might be 3. But then we're kind of done with that story. So how might we do it a little better? Well, let's start again at 0. Here might be 1. Why don't we call this 2? Why don't we call this 3? Why don't we call this 4? Call this 5, this 6, and this 7. Now, it's fine if you didn't quite see what pattern I was following, but take my word for it that that was a unique pattern of light bulbs. 8 total times. I started it off, 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 and I ended it on, on. But along the way, there were indeed 8. But how high can I count? Well, it kind of depends on what number you start counting from. And just as we thus far have been doing, computer scientists do all the time. Computer scientists, and in turn computer programs, typically start counting from 0 just because it makes sense, because when everything is off, you might as well call that 0. So if we start counting at 0, and we have 8 possible patterns that we just saw pictorially, well, that would allow us to count as high as 7. So from 0 to 7, so 7 is the highest we can count with 3 light bulbs. So those of you who proposed that 7 was the answer, 36% of you were indeed correct. 57% of you who said 8 are correct if you assume we start counting at 1, and that's fine, but at least in the computing world now, we'll generally by convention start counting from 0. But you are correct to say that there's 8 such possibilities. All right, well, this is all fine and good to represent things with patterns of light bulbs, but how do we actually now get to the zeros and ones that a computer is actually using? Because what's inside of a computer at the end of the day are not light bulbs, but tiny, tiny little switches, millions of little switches that can either be on or 1 or off or 0. Those switches happen to be called transistors. And these days, computers do have millions of these things that can be on and off in different patterns. So if you have the ability to turn on and off all of these switches, well, what can we all agree on representation when it comes to using those switches? How will we represent information with them? Well, wonderfully, we don't really need to think very hard or go past our very comfortable roots as kids if we consider for a moment not just 0 and 1, but the whole decimal system, 0 through 9, that you and I all started our day with today. How does that system work? Well, here on the screen is 1, 2, 3. So yes, you're probably thinking that's 123, but not quite. All I've shown on the screen is a pattern of symbols, 1, 2, 3, or 3 digits. And all of us probably are instinctively just saying, obviously, it's 123. But it's probably been years since you considered why it is 123. Well, let's consider what each of these digits or symbols represents. If you're like me, you grew up learning that the rightmost digit is the ones place, the middle is the tens place, the left one is the hundreds place. And so how do we get from these 3 symbols or digits, 1, 2, 3, to the mathematical idea we know as 123? Well, all of us instantaneously these days did 100 times 1 plus 10 times 2 plus 1 times 3, which of course is just 100 plus 20 plus 3, or the mathematical value we all know as 123. So a bit of a circular argument, but just to remind us how we got from 123 to 123. Well, it turns out that in the world of computers, the system they use is exactly fundamentally the same. The only difference is that computers only have access to zeros and ones, not zeros through nines. So if we consider now, in the abstract, just 3 possible digits represented here, let's consider for a moment why those columns or places were 1, 10, and 100, and so forth. Well, why was that the case? Well, there was a pattern, in fact, and it just has to do with exponents or powers. So the rightmost column, technically, if we really get into the weeds, is 10 to the 0th power, which, if you recall, just means 1, 10 to the 1st power, which is just 10, and 10 to the 2nd power, or 10 squared, is 100. But what's interesting about representing it in this way is that it jumps out that 10 is involved. There's 10 digits, 0 through 9, so the columns are using this base of 10. So you can perhaps now get even ahead of me here by considering, well, if in the binary system that computers use, you only have 2 digits, zeros and ones, odds are the only thing that's going to change is the meaning of these columns. Now we have the ones place still, because 2 to the 0 is 1, but then we have 2 to the 1st, 2 to the 2nd, and so forth. And of course, if we just do out that math, in the world of binary that computers use, we have the ones place, twos place, fours place, and so forth. And now we're good to go. Even though we have to now think in a different base system, now we can start counting more properly. And now we can move away from the metaphor of light bulbs and consider that if all of those light bulbs are off, we're again just going to start thinking of those things as zeros. So that would be a pattern of symbols or digits that's 0, 0, 0 in binary. But in our human world, the mental math you would probably do now instantaneously after today would be, well, that's obviously 4 times 0 plus 2 times 0 plus 1 times 0, or of course 0 in decimal. But how does a computer represent the number 1, for instance? Well, it's just going to change that rightmost bit from a 0 to a 1. Or, more metaphorically, it's going to turn that switch on and illuminate that rightmost light bulb, just like I did earlier. How do I represent 2? It's going to be 0, 1, 0 in binary. How do I represent 3? This is where we're about to differ. Now I'm putting on 2 of those switches because I need something in the 2's place and the 1's place to give me mathematically 3. Next, if we go ahead and choose count up to 4, that's going to be 1, 0, 0. If I want to count up to 5, that's going to be 1, 0, 1. 6 is going to be 1, 1, 0. And finally, the number 7 is going to be 1, 1, 1. So it would seem that using 3 bits, each of which can be a 0 or 1, yes, you can permute them in 8 different ways. 2 possibilities for the first, times 2 for the second, times 2 for the third gives us 8. But as per this math and the intuition of starting counting from 0, we can only count up as high as 7 in total. Well, let's go ahead and actually take this out for a spin. When we don't have just, say, let's say, 1 light bulb or 3 light bulbs, we have actually the fortune of having like a whole stage worth of light bulbs. 64 light bulbs adorn the stage here. And you know what, Sumner, could we go ahead and put up a random number on the screen here? All right, so if you can see these light bulbs from your perspective, we have 8 light bulbs plus another bunch of them off, and all the others are off. So let's go ahead and ask a question then. If these light bulbs now represent not just 1 light bulb or 2 or 3, but several more, in this case at least 6 light bulbs, what value do we actually get? Well, let me go ahead and put a question on the screen here, which should pop up on yours in just a moment. And you should see now on your end this same question put in binary terms. What number in decimal does binary number 110010 represent? What decimal number does binary number 110010 represent from left to right? So here we have an overwhelming response. 50 is indeed the correct answer. Now, why is that? Well, if I go over to the physical light bulbs here, let's just consider for a moment what the pattern actually is. This here is the 1's place, the 2's place, 4, 8, 16, 32. And we could keep going, but it's not going to matter because they're all off. So we have 32 plus 16 plus 2, which indeed gives us the number you and I know in decimal as 50. And just imagine how high we could count with all of the other light bulbs as well. All right, so we started with the story with electricity.